Hello, welcome. In this short video, let us look at the theorem that the nth moment of a probability distribution is equal to the nth derivative of the moment generating function at s equal to 0, where s is the parameter of the moment generating function. So basically, we want to prove that the nth moment expectation of x power n, it is where x is the random variable, is given by the nth derivative, that is dn by ds power n of the phi x of s, where phi x of s is the MGF, that is moment generating function, at s equal to 0. So this is the theorem we want to prove. By definition, the moment generating function phi x of s is equal to expectation of e power sx. Therefore, phi x of s is equal to integral e power sx into fx of x dx. Now clearly, by differentiating both sides with respect to s one time, we get d by ds of phi x of s is equal to integral x into e power sx fx of x dx, because the only term that is a function of s is e power sx, so its derivative is x into e power sx. But this is at s equal to 0, that is d by ds, the derivative of phi x of s at s equal to 0 is nothing but, when we put s equal to 0 here, we get integral x fx of x dx. So this is nothing but, by definition, equal to expectation of x, that is the first moment. And clearly, by continuing the differentiation process n times, we can clearly see that d power n by ds power n of phi x of s is equal to integral the nth derivative of this function, that is phi x of s is equal to integral the expectation of e power sx is nothing but x power n into this function. Only factor, that is function of s, is e power sx, so its nth derivative is x power n into e power sx, because it is an exponential function. So we have x power n into e power sx into fx of x dx. But at s equal to 0, clearly the nth derivative of phi x of s at s equal to 0 is equal to integral x power n fx of x dx, since this is 1 for at x equal to 0. So this is nothing but, by definition, expectation of x power n, that is nth moment of x, nth moment of the probability distribution of x. Therefore, expectation of x power n, that is nth moment corresponding to the probability distribution of x, is equal to the nth derivative of the moment generating function phi x of s at s equal to 0. Now let us look at an example illustrating this theorem. So given the following PDF, that is the probability density function, fx of x is equal to lambda into e power minus lambda x greater than or equal to 0 and 0 elsewhere. So this is the exponential distribution. So given this exponential distribution, we want to find its moments through the MGF. That is, we want to find expectation of x, which is given by the first derivative of phi x of s at s equal to 0. But phi x of s for this function is expectation of e power sx, which is equal to integral, and this function is only valid for x greater than or equal to 0, so we have x equal to 0 to infinity e power sx into lambda into e power minus lambda x dx, and this integration basically results in lambda into e power minus lambda minus s of x divided by lambda minus s minus of lambda minus s, and this integral becomes 0 to infinity. At infinity this is 0, at 0 this is 1, so we are left with lambda by minus 1 by minus of lambda minus s, which is equal to lambda by lambda minus s. Therefore, this is the moment generating function for this given PDF. Or by using this result, we can derive the moments of this function fx of x, that is the exponential PDF. That is, for example, the first moment is given by the first derivative d by ds of lambda by lambda minus s at s equal to 0, which is equal to the derivative is lambda into minus 1 by lambda minus s whole square into minus 1, which is equal to lambda by lambda minus s whole square, and at s equal to 0, this is basically equal to lambda by lambda square, which is 1 by lambda. Therefore, expectation of x is equal to 1 by lambda. And similarly, we can derive the expectation of x square as the second derivative d square by ds square of lambda by lambda minus s at s equal to 0, which is equal to lambda by basically minus 2 into minus 1 by lambda minus s by lambda minus s whole cube. At s equal to 0, this becomes lambda by lambda cube, that is 1 by lambda square. This becomes 2 by lambda square. And finally, expectation of x power n, that is the nth moment of this given PDF, is equal to the nth derivative of this MGF at s equal to 0, which is and the nth derivative of the given function is nothing but lambda into n factorial by lambda minus s by power n plus 1. At s equal to 0, this becomes n factorial by lambda power n plus 1, lambda by lambda power n plus 1, which is lambda power n. So this is the nth moment of this given PDF, and we can clearly see that it is very easy to use the MGF function to derive the moments of a PDF. Thanks for watching.